Your brand new electric vehicle just lost 20% of its range overnight. The temperature dropped to 30 degrees, and suddenly your 300-mile range became 240 miles. But that's not even the worst part. The worst part is what happens to that battery pack sitting underneath your car over the next 5 to 10 years. Because while car salespeople are talking about zero emissions and government tax credits, they're not telling you about the $15,000 surprise waiting in your future. Battery degradation. The slow, inevitable reality of any EV's most expensive component. And if a buyer doesn't understand how this works before signing that lease agreement, they are about to make a very costly mistake. Here is the part the dealership skips entirely. And it starts with data the automotive industry hoped you would never go looking for. Based on extensive industry reports, thousands of diagnostic teardowns, and independent engineering investigations into the electric vehicle market, the data is entirely clear. We have seen the internal service bulletins. We know exactly what happens chemically and mechanically when these massive lithium-ion battery packs hit year 6, year 7, and year 8. And we have watched too many consumers get blindsided by out-of-warranty repair bills that end up costing more than the residual value of the car itself. So let's start with the basics. Every major electric vehicle on the road today uses some variation of lithium-ion battery technology. These batteries are made up of thousands of individual cells, usually arranged in modules, all connected together to create the massive, heavy battery pack that powers your vehicle's electric motors. These battery packs are genuine marvels of modern engineering. A Tesla Model S battery weighs about 1,200 pounds and contains over 7,000 individual battery cells wired in complex series and parallel configurations. A Ford Mustang Mach-E battery pack stretches nearly the entire length of the vehicle's floor, acting as a structural component of the chassis. These aren't the same simple batteries sitting in your smartphone or your laptop. We're talking about sophisticated, liquid-cooled thermal management systems, advanced battery monitoring computers that track the voltage of every single cell, and protective shielding designed to withstand massive impact. But here's the unavoidable problem of battery chemistry. Every time you charge your electric vehicle, every time you discharge it by accelerating onto the highway, and every time the ambient temperature drastically changes, those battery cells undergo physical and chemical stress. And unlike your traditional gas tank, which fundamentally works the exact same way on day 1 as it does on day 3000, your battery pack is slowly losing its maximum capacity from the moment it leaves the manufacturing plant. The first major concept you need to understand is thermal runaway and the heat management required to prevent it. Lithium-ion batteries naturally generate significant heat during both charging and discharging. When these battery cells get too hot due to extreme stress, manufacturing defects, or external damage, they can enter a state called thermal runaway. This is a catastrophic failure mode where the internal heat causes chemical reactions that create even more heat, which causes further rapid reactions, cascading from one cell to the next. This is exactly what happened to several Chevrolet Bolt owners, whose vehicles tragically caught fire while parked in their garages. The National Highway Traffic Safety Administration had to open a massive investigation, and General Motors ultimately had to recall every single Chevy Bolt ever made. We're not just talking about a small batch of defective cars. We are talking about over 142,000 vehicles recalled worldwide. The root cause was traced back to 2 rare manufacturing defects from their battery supplier, LG Chem, a torn anode tab, and a folded separator within the same cell. This massive recall forced GM to spend nearly $2 billion to replace complete battery modules, highlighting exactly how sensitive and volatile these dense energy storage systems can be if the manufacturing tolerances aren't absolutely perfect. But catastrophic thermal runaway isn't the only temperature issue. Extreme heat is also one of the main reasons your battery degrades over time. Every time you park your EV in direct, baking sunlight on a 90-degree day, And every time the thermal management system has to work overtime to keep temperatures controlled, you are testing the limits of the battery's chemical stability. Now, early in the EV transition, there was a widespread belief that using DC fast charging networks, like Tesla's superchargers, would rapidly destroy your battery. Older data suggested that the massive influx of electricity and the resulting heat generation would literally break down the chemical structure inside the battery cells. However, we now have a much clearer, data-backed picture. Recent large-scale, independent studies analyzing over 12,000 electric vehicles have shown that frequent fast charging does not significantly accelerate long-term degradation compared to home charging. But there is a massive catch. This lack of degradation is entirely dependent on the vehicle's active thermal management system working flawlessly. Modern EVs use a process called preconditioning. When you route your navigation system to a fast charger, the car intentionally uses the electric motors to generate waste heat, warming the battery coolant to the perfect optimal temperature before you ever plug in. Then, during the 30-minute charging session, powerful air conditioning compressors chill that same coolant to prevent the battery from overheating. If this complex thermal management system fails, or if a manufacturer uses inferior passive air cooling instead of liquid cooling, that high-current fast charging will absolutely cause accelerated, permanent chemical breakdown inside your cells. The second major issue impacting your range is something called calendar aging, and it happens even when your car is sitting perfectly still in a climate-controlled garage. Lithium-ion batteries age based on the simple passage of time, not just your daily usage. That brand new electric vehicle sitting on the dealer lot has technically been losing a fraction of its capacity since the day the battery cells were manufactured and sealed. Long-term studies from institutions like the National Renewable Energy Laboratory show that lithium-ion batteries naturally lose a small percentage of their capacity per year strictly from chemical aging, regardless of how many miles you drive. Over time, parasitic chemical reactions inside the cell cause the continuous growth of the solid electrolyte interphase (SEI) layer on the anode. As this layer slowly thickens over the years, it traps active lithium ions, permanently removing them from the energy-generating process. This means that after 10 years, even if you barely used your electric vehicle and kept the mileage incredibly low, your battery pack will have inevitably lost a noticeable percentage of its original factory capacity. Imagine buying a traditional combustion engine car that started with a 20-gallon fuel tank, but simply because 10 years had passed, the physical size of that tank had shrunk and could now only hold perhaps 16 gallons. That is essentially what happens with the chemical storage of EV batteries. Except you can't just unbolt a fuel tank and swap in a new one for a few $100s. The third operational problem is depth of discharge damage. Most major EV manufacturers explicitly recommend keeping your daily battery charge level between 20% and 80%. But here's what they often fail to explain clearly to new buyers. If you regularly charge your vehicle to a full 100% and let it sit there, or if you regularly drive the battery down to near 0%, you are placing immense voltage stress on the internal chemistry. Charging a traditional nickel-manganese-cobalt (NMC) lithium-ion battery to 100% puts maximum physical stress on the cathode materials. Letting the battery drop to near zero creates a different kind of voltage stress that can dissolve copper from the current collectors, permanently reducing the cell's capacity and increasing its internal resistance. Yet, many new EV owners simply plug their cars in and charge to full every single night because that is exactly what we have been trained to do with our smartphones. Research from multiple automotive engineering programs confirms that standard lithium-ion batteries last significantly longer and retain much more of their original capacity when strictly kept between that 20 and 80% threshold. But this creates a very real practical problem for the consumer. You are effectively only using 60% of your battery's expensive, advertised capacity for your daily driving needs. That highly marketed 300-mile EPA range rating instantly becomes just 180 miles of actual usable daily range if you want to follow the engineering best practices for maximum battery longevity. Now, let's talk about cold weather performance, because this is where the daily reality gets highly problematic for electric vehicle owners living in northern climates. Lithium-ion batteries temporarily lose significant usable capacity in freezing temperatures. We are not talking about a small 5% decrease. At 0 degrees Fahrenheit, depending on the heating system the car uses, most EV batteries lose up to 40 to 50% of their effective range. The American Automobile Association extensively tested several popular electric vehicles in 20-degree weather and documented range reductions averaging over 40%, largely because heating the passenger cabin uses a massive amount of electrical energy. Norwegian automotive organizations have found similar results during extreme winter testing, with some poorly optimized vehicles losing half their range. But here is a critical engineering correction regarding cold weather. The battery does not automatically degrade just by existing in the cold. The true danger, and the cause of permanent degradation, occurs when you attempt to charge a freezing cold battery. When lithium-ion cells are subjected to freezing temperatures, the chemical reactions slow down drastically. If you try to force high-voltage charging into a cold battery, the lithium ions cannot easily absorb into the graphite anode. Instead, they pile up on the surface of the anode and turn into metallic lithium. This phenomenon is known as lithium plating. Lithium plating permanently destroys battery capacity and can even create internal metallic spikes, called dendrites, which can cause short circuits. To prevent this catastrophic damage, modern electric vehicles rely on sophisticated software that intentionally restricts and heavily throttles your charging speeds in the winter until the internal battery heater has spent significant time and energy physically warming the massive battery pack. So while the cold won't inherently destroy a parked battery, it severely restricts your vehicle's usability, slashes your range, and forces extremely long wait times at charging stations during the winter months. Here is where the financial reality of all this degradation hits the hardest. When your EV battery eventually degrades to the point where it fundamentally needs replacement, you are looking at hardware and labor costs that can easily exceed the actual resale value of your aging vehicle. A completely new replacement battery pack for a high-end vehicle like a Tesla Model S generally costs between $12,000 and $20,000 out of pocket. A replacement battery pack for a Chevy Bolt or a Nissan Leaf can easily run between $10,000 and $16,000. These are not arbitrary dealership markups or inflated local repair shop prices. These are the actual, baseline hardware costs of these massive, resource-heavy battery packs sourced directly from the manufacturers. Furthermore, the specialized labor required to safely drop an old high-voltage battery pack and properly install and program a new one adds another $2,000 to $3,000 to the final invoice. Think about this strictly from a long-term financial perspective. If you purchase a $40,000 electric vehicle, and after 8 or 9 years you are suddenly faced with a $15,000 battery replacement just to keep the car functional, you have essentially lost a massive percentage of your vehicle's total value to a single, inevitable component failure. No traditional gas engine or transmission repair comes remotely close to this kind of guaranteed, high-dollar replacement cost. The automotive industry will heavily promote the idea that battery manufacturing costs are coming down every year, and wholesale costs are indeed dropping. But retail replacement costs for consumers are not dropping fast enough to make repairing an 8 or 10-year-old mainstream EV economically viable for the average second or third owner. Which brings us directly to the recycling situation. Lithium-ion batteries contain highly valuable and critical materials, including nickel, cobalt, lithium, and copper. For years, critics cited outdated statistics claiming that only about 5% of lithium-ion batteries were actually recycled, leading to massive environmental concerns about landfill waste. However, the recycling industry has advanced dramatically. Today, specialized recycling companies utilizing advanced hydrometallurgical processes are capable of taking dead battery packs, shredding them down into a substance called black mass, and successfully recovering up to 95% of the critical battery metals. The recovered lithium, nickel, and cobalt are often pure enough to be sent right back into the manufacturing supply chain to build brand new EV batteries. The true problem we are facing today is not the chemical ability to recycle the batteries, it is the sheer logistical nightmare and immense cost of transporting them. You cannot simply drop a degraded 1,000-pound high-voltage chemical battery into the mail. Dead EV batteries must be handled under strict Class 9 hazardous materials regulations. Shipping these massive packs safely from thousands of local dealerships across the country to the few centralized, high-tech recycling facilities is incredibly expensive and slow. The infrastructure to handle the fast-approaching wave of millions of dead EV batteries simply does not exist at scale yet, creating a massive logistical bottleneck. Let's also look at the public charging infrastructure, because this directly impacts how you'll be forced to use your EV battery. The United States currently has tens of thousands of public charging stations compared to over 150,000 gas stations. But raw numbers don't tell the full story. The real problem is charging speed, availability, and hardware reliability. Most widespread public charging stations are Level 2 chargers, which utilize alternating current and generally add only about 25 miles of range per hour of charging. That's highly useful for destination charging at a hotel or an office, but absolutely useless for highway road trips. DC fast chargers are required for road trips, but there are far fewer of them nationwide. And as we discussed earlier, relying exclusively on fast chargers requires your vehicle's thermal management system to be working absolutely flawlessly to prevent accelerated degradation. Furthermore, non-Tesla charging station reliability remains a severe issue. Independent studies and government surveys frequently find that roughly 20% or more of public charging stations in major metropolitan areas are non-functional at any given time. These are high-voltage, liquid-cooled electrical cabinets that cannot be fixed by a gas station attendant with a wrench. They require highly specialized technicians and specific proprietary replacement parts that can take weeks or months to arrive.